So my name is Richard Dang. I'm in Group 1, and I'm the group lead for the bomb calorimeter experiment. So what is a bomb calorimeter? It's basically a device that measures the heat produced by combustion of a fuel sample. So in short, we're going to have a fuel placed in this crucible. It's going to ignite, therefore releasing heat in this controlled volume. And then the water's going to heat up, and we're going to measure the change in temperature difference for the thermometer. And then we're going to calculate the heat. So the main objectives of the bomb calorimeter is to learn the theory, principles, and the techniques behind the bomb calorimeter. We're also going to determine the thermal capacitance of the bomb calorimeter, which is made of stainless steel and the water in the water tank. And we're also going to determine the gross heat of combustion samples. And in this experiment, we're going to be combusting 1 gram of benzoic acid and 1 gram of a mystery substance. So the theory behind the bomb calorimeter, so basically the bomb calorimeter measures temperature change because of the combustion. We can use the first law of thermodynamics to derive this equation. Q equals M times CV times delta T. And basically energy in, energy out. The energy released by the fuel combusting is going to release into the water, into that controlled volume. And we can change this equation to make it fit better for what we're going to calculate later. So it's M times CV equals Q over delta T. Q is going to be the heat of combustion produced by the combustion, and MCV is going to be thermal capacitance, which is basically the mass of what we're calculating times the specific heat of the control volume, and delta T is the temperature rise in the water. So this is the basic apparatus we'll be using. So as you can see right here, number 6 we have right here, we have the thermocouple, which is going to measure the temperature of the water throughout the entire experiment. It's going to connect to the DAT, which is used to measure our data. We're going to have number 2 right here, which is going to be the stainless steel bomb. And we have number 7, the water stir. The water stir's main purpose is to basically make sure the water keeps moving, make sure the temperature stays even throughout the entire mixture, because if we didn't have a water stir, we would have, like, say, uneven temperatures in the water all around. Like closer to the water, closer to the bomb, the water would be hotter, and further away it would be colder. So we want to make sure the temperature's even throughout. And we have a water bucket holding the water, which the stainless steel bomb is placed inside, and then outside of that we have the jacket. It was used to insulate the entire bomb calorimeter. And you can see right here we have the detail of the bomb. Basically, the electrodes connected to the wire, which is used to combust our fuel, which is held in the crucible right here. And we have to make sure that wire does not touch the crucible. And we also have our relief valves and our check valves, which is used to basically bring in oxygen for the combustion to be complete. And the basic procedure is we're gonna place our fuel inside the crucible and then place the wire touching the electrode terminals, but not touching the crucible so it doesn't short it out. And then we're gonna place that fuel sample into the bomb calorimeter, the bomb. We're gonna close the sleeve, tighten it all the way down, and then we're gonna add oxygen into the bomb, and then we're gonna purge it and add oxygen again, and then purge it and add oxygen again to 30 atmospheres. And then what's basically gonna do is basically flush all the gases we don't want inside. So we want basically pure oxygen to ensure we have a complete combustion reaction. Like we have no leftover fuel, and And then basically after we combust it, we're gonna measure the change in temperature of the water and use that values to calculate our Q. So right here we have sample calculations and expected results. So for our case, we're gonna have a system of 2 kilograms of water and 3 kilograms of stainless steel. So we can use the thermal capacitance of the system is going to be equal to the thermal capacitance of the water plus the thermal capacitance of the stainless steel bomb sleeve. And we get 2 kilograms of water times the specific heat of water, which is 4,184 joules per kilogram. And we have 3 kilograms of stainless steel times the specific heat of 500 joules per kilogram, and we get approximately 9,868 joules per Kelvin for the thermal capacitance of the system. And then to predict the temperature rise for our fuel, we have 1 gram of benzoic acid, and we estimated the Q to be around 26,400 joules per gram, which is found off Google. And then basically you plug in all our numbers into the equation, and we get delta T equals Q over the thermal capacitance of the system. You get 26,400 joules per gram times the unit mass of 1 gram divided by the thermal capacitance of the system, and we get approximately a 2.67 increase in Kelvin temperature of the water. So there are a lot of potential sources of error for this experiment. So say we have an incomplete seal from the jacket to the bomb in the outside air, like leading to temperature leaks inside the bomb in the water to the outside air. So the readings could be slightly lower. And we could also have incomplete combustion, which could be due to the lack of doing, like, say, the necessary amount of purges we had to do was 3 purges for the oxygen. So, like, say if we only did 1, we wouldn't have enough oxygen for the complete combustion reaction, meaning we had a leftover fuel, and we wouldn't get the expected temperature rise. And we could also have improper wire contact, meaning a wire could have shorted. And we have user error, which is if we waited too long for the temperature to reach equilibrium, we would have like a loss in temperature. And the importance of it is that the bomb calibrator is that we can evaluate like fuel constants. Like say we want to measure how much energy, if we combust this fuel, how much energy will be released per unit mass, and we can determine if it's going to be efficient or not. And that's all I have. Any questions?